All right, so welcome back to episode 5. We're going to do another example for composite functions, but this time talking about domain restrictions a little more. And in order to do an example with that, I had to use some fractions, which we don't really like, but that's where domain restrictions happen. So this video will probably be a little bit longer because I'm just going to do this all in one swoop, and so I hope you stick with me. So starting with the first part here, we have 10 rabbits, which are set loose on an island. Their population growth can be approximated by the function p of t, and then we give you p of t. And so p represents the rabbit population t years after they were set loose. So relationship between population and time. And a little bit more word problem here. So we have function s, which denotes the percentage of spotted rabbits on the island as it relates to the total population of rabbits. And then we got a little function there. All right. So the first thing that we're going to do is find s of p of t and explain the meaning. I really debated putting you guys through the algebra here, and I don't think I will, but I will show you kind of where you would go with some of the math. I just think it's a little complicated. I didn't mean for it to be. So we can also write it this way, s of p of t. So anywhere that we see p, we have to plug in p of t. So that is going to equal, p is right there. Let's go back to our p of t. Looks like that. Going to use the power of memory. So 60 times t plus 1 over t plus 6. Now you're starting to see how messy this gets. Subtract 15. And then we have to do this again on the bottom. T plus 6 minus 10. Okay, so let me just tell you kind of what I did here. Basically, you would have to get a common denominator on the top and bottom. So you would get one fraction on the top, one fraction on the bottom. They have a common denominator of t plus 6, so that would end up canceling out. And you would just have a numerator and a denominator. It's a little bit messy. I don't think you're going to have to do anything of the sort. So let me look at the answer. The answer I got was 45t minus 30 over 50t. All right, so that would be the simplified version of, let me write this out, s of, wait, no. Here, let's write it this way. S of p of t. That's what that is. And that's good because we should just see time in this equation. We shouldn't see any p's. And let's go to the part that we really want to focus on here, which is the domain. And I think it would have been a waste of time for me to just explain this verbally without an example versus just working it out with the example. So that's what I'm about to do. So again, I'm going to rewrite this. S of p of t. So let's talk about domain. We know about domain as just the valid inputs, the numbers that you can put into a function and you can actually get something out of it. And typically that gets a little bit messed up when you have fractions because the bottom of a fraction cannot equal 0. So that is why I chose this example. But talking about compositions, initially you're going to plug in a t value into P of t in this case. So we know that whatever t we choose, I think that's the domain sign, I'm not sure. T needs to be in the domain of P of t, right? Because if it isn't, then we're not going to get an output, and then we have nothing to plug into S. So T needs to be in the domain of P of t. And then, so we're going to get a result there. And so whatever that result is needs to be in the domain of S, because if it isn't, then we're not going to get an outcome. So P of t needs to be in the domain of, I guess, yeah, I'll just write that as S of P. Okay, so essentially we need t in the domain of the first function, and then whatever we get there needs to be in the domain of the outside function. So how do we use this information? Well, basically we need to find the valid outputs for P of t, first of all, because that's the inside. So if we look at this function here, we see that t cannot equal -6. More importantly, we have to pay attention to context. And we know that t represents time, and we can't have negative time. So t is going to have to be greater than or equal to 0. And that's really our only restriction for that one. So first of all, t needs to be greater than or equal to 0. So that's one domain restriction. And then we also need to look at the domain of S of P, so the valid inputs for that function. And then if there are any invalid ones, we need to make sure that P of t does not equal those values. And we see that again on the bottom of the fraction here. P cannot equal 10. Okay, so which tells us the function for P of t cannot equal 10. It looked like everything else is, is doable, but that was the one restriction. So let's look at the function for P of t. You probably don't want to look at it. It's a little bit weird. So it looked like this. And we do not want that to equal 10. So we have to figure out the t value that would make it equal to 10. And remember how we initially had 10 rabbits in the population? So that's at t equals 0. So when t equals 0, this function is 10, which we don't want it to be. So t cannot equal 0 in that case. And then all we have to do is just combine these two restrictions here. So in the first part, t was greater than or equal to 0, but we just figured out that t can't be 0. So really, t must be greater than 0 for this composite function. Okay. And then I also like to check the composite function itself to see if there are any other restrictions in that function. And so this was the result we found here, and it looks like t just, it can't be 0, right? And anything greater than 0, it's going to give us a positive number, which we want as a percentage. So that all checks out. That's our domain, folks. So the process here, you want to find the t-values that work for the inside function. And then you want to see the domain of the outside function and figure out if there are any invalid outputs there. And then you're going to set the inside function equal to those numbers to figure out the t-values that would have created that result that we wouldn't want. It's a lot of talking, I know. Okay. And then I'm just going to go through these relatively quickly, but another way that you're going to see compositions is on like a table or a graph. So I just want to kind of give some exposure to that. This table took me forever. Please appreciate it. Anyways, given the values above, we want to find S of P of 4. All right. So first things first, we want to know what P of 4 is. So let's look at our P function in the second row here. P of 4 is going to equal 30. So now we're trying to find S of 30. So we go to our S function at the bottom here, and then we have some P values. So P, when that's equal to 30, we have an S value of 75%. So using the tables is really just practice. It's not too complicated. So let's do one more. S of P of 9. So first we need to find P of 9. Can I write on the table? Whoa, I can. Very cool. Okay, P of 9 is going to be right here, 40. And then so we need to find S of 40. So S of 40 is going to give us 83%. All right, and then last thing, I want to show you what that looks like on a graph. So this is what happens when we graph both of these functions and we apply domain restrictions and everything. So we want to find S of P of 4. I know we just found that, but we're going to find it a different way. S of P of 4. So first let's go on the graph of P and find what P of 4 is. So 4 is right here. Run that along. And on the graph here, we get 30. S of 30. All right. And then so our input is 30. We need to find what S is equal to at 30. And then normally you'd be able to zoom in there. It looks like it's less than 1. It's about like 0.75. I didn't cheat, I promise. So like roughly 75%. And so that would be the way to do those calculations, like with a table or with a graph. Okay, and that's it for composite functions. Thank you for sticking with me, and I hope you learned something.